Today we're going to talk about some subclassifications of force. And the ones we're going to talk about today include friction, drag, and elasticity. First of all, let's start out by talking about friction. What exactly is friction? Friction is the force that opposes the relative motion of any two systems that are in contact with each other. What you can see here in the diagram is friction is generally the result of an incongruity between the two surfaces that causes them to resist motion between each other. Now, friction can be broken down into two types of friction. The first type is called kinetic friction, and that is the friction or the force that opposes motion when the two systems are in contact with each other and are in motion relative to each other. The other type of friction is called static friction, and that friction is the force that opposes motion between two systems that are in contact but are at rest relative to each other. As you probably know just from experience, static friction is higher, or there is more friction force when the two systems are at rest relative to each other, as opposed to when the kinetic friction or dynamic friction, when they're actually have already begun to move relative to each other. This can be experienced whenever you're pushing something along the ground. To get it started requires more effort than to keep it moving once you have it moving. Now, the magnitude of static friction, or F sub s, is equal to a factor known as the coefficient of static friction times what's known as the normal. And I've spoken about the normal before. The normal is the force that is generated perpendicular to the surface of the object. So what we have here is the static friction force, the coefficient of static friction, and the normal force. Kinetic friction is exactly the same, except now it's the coefficient of kinetic friction as opposed to the coefficient of static friction. And the coefficient of kinetic friction is always less than the coefficient of static friction. Now here we have an example problem. Let me read the problem to you and then we'll do it. You have a skier, and we've seen this skier before. He has a mass of 65 kilos. He is sliding down a slope with an angle of 25 degrees. If the kinetic friction force is 45 newtons, what is the coefficient of kinetic friction? Okay, let's write the formula that we used in the past. F is equal to kinetic friction times the normal. This is also written mu sub k times the normal. The normal in this case, from last week, we know that the normal is equal to the weight times the cosine of the angle theta, which in this case is 25 degrees. So the normal is going to equal 65 kilograms times 9.8, which is the acceleration due to gravity, times the cosine of 25 degrees. And if you do the math here, you get 577.318 newtons for the weight. So if you rearrange this so that you can calculate this coefficient, the coefficient of kinetic friction is going to equal to the friction force divided by the normal, which is going to be 45 divided by 577.318. If you do that math, you get 0.0779. There are no units for this calculation because you're dividing one force. This is the norm newtons and this is newtons, and these cancel each other out, and coefficients generally do not have a... When two rough surfaces are in contact with each other, there is a relationship between the surfaces that are in contact. So when two rough surfaces in contact have a small area of actual contact than their total area, then there's a smaller normal force, and this results in a smaller friction force. When two surfaces are in greater contact, then there's a greater normal force, and this results in a greater amount of friction. Here's another problem that we can work on that is very similar to the previous problem. What we have here is an 85 kilogram ice skater that's being pushed by two other people. The total is a conglomerate of the force of the first person and the force of the second person. The force of the first person is 34.2 newtons. The force of the second person is 23.3 newtons. So we can find the total force with that. If the coefficient of static friction is 0.4, what would the acceleration of this person be in the direction of F total? If she is already moving, then we have to calculate her based on her coefficient of dynamic friction or coefficient of kinetic friction, which is 0.02. What would be her acceleration then? First of all, to find the total force, F total is going, F total squared is going to equal F1 squared plus F2 squared by Pythagoras' theorem. So that means that F total is going to equal the square root of F1 squared plus F2 squared. And let me move this over this way so that you can see where I get this. You can see that F1 and F2 are here, so that F1 squared plus F2 squared is going to be F total squared. So if we put the numbers in, the square root of 34.2 squared plus 23.3 squared, and working this out, you get 41.1 newtons. So the total force that these two ladies are exerting on their friend here is 41.1 newtons in this direction. Now, since the question has to do with in the direction of F total, we don't actually have to calculate that angle, but we could if we needed to. But we know that the static friction that's acting on this lady at this time is going to equal the coefficient of static friction times her normal. And her normal in this case is equal to her weight, since she's standing upright on the ice. So this is going to equal 0.4 times 9.8 is the acceleration due to gravity, and her mass was 85 kilos. And if you calculate this out, you get 333.2 newtons. That means that this much force is necessary to get her moving, and this is considerably less. Therefore, she doesn't move. So there's no acceleration. Now, the static or kinetic friction, it's the second part of the question is, what if she's already moving? Then what is her acceleration? This formula then changes in the fact that we now use the coefficient of kinetic friction instead of the coefficient of static friction, which in the problem was 0.02. The normal is the same, when you do the calculation, the kinetic friction is 16.66 newtons. So that means now you can see that she's being pushed with this force, and this is resisting. So the acceleration that she has is going to be what's left after you overcome the kinetic friction force. And so the force that's driving her or accelerating her is going to equal the 41.1 newtons the two girls generate minus her friction force. So that's going to equal 24.74 newtons. And then if you divide her mass into this number, so if you take 24.74 and divide her mass into that, you get her acceleration, which is 0.291 meters per second squared. Let's talk briefly about drag forces. Drag forces are the force that oppose motion in an object, but unlike friction, drag is proportional to a function of the velocity of the object in the medium of motion. And I'll show you what that means in just a second. So here we have an airplane, and here is how you would calculate the magnitude of the drag force on this airplane. This is the formula, which is also in your book, that gives the extent of the drag force. And here are what each of these symbols mean. The drag force is equal to 1/2 times the coefficient of drag, which is a function of the medium that you're in, the density of the medium, the area of the object passing through the medium, that is the cross-sectional area that passes through the median, and then the velocity of that object. And so whenever you have an object that passes through, sometimes this part right here is a constant called B, in which case the drag force is equal to a constant B, which is 1/2 C rho A and times V squared. But if you remember this, and in your book there's a table that gives these coefficients of drag depending on the type of medium that you're in. There's something called the terminal velocity that you'll hear about from time to time, and that's when the drag force is equal to the weight of the individual falling. When that occurs, then acceleration stops, and that's why it's called the terminal velocity. The person cannot accelerate any longer. There's another law about drag which states that the general application of drag does not apply if the object is very small or in a denser medium than air. That is, if the object is extremely small, then drag is not taken into account. It is so inconsequential that it is not taken into account when it's fallen. So for example, if you drop a grain of sand, you don't have to calculate the drag in that situation.